Coming to ideal transformer, the two coils are completely pure without any losses. Lossless core. Lossless core means hysteresis loss and eddy current loss. These two are completely zero. Reluctance offered by the core to the magnetic flux, that is also zero. Permeability of the core is infinite. Leakage flux is zero. The two coils are having zero resistance. Copper losses will be completely zero. Flux in the core is always maximum flux or main field flux. The magnetizing current required to establish this main field flux is zero. That means without any magnetizing current, flux in the core will reaches its maximum value 5m. pH curve is completely linear. MMF, magnetomotive force, required magnetomotive force is 0. Load power factor equals to source power factor. Power transfer from primary to secondary is same. Transformation ratio K, V2 by V1, E2 by E1, N2 by N1, I1 by I2. E2 by E1, N2 by N1, this can be taken as internal ratio when the supply is not given to the transformer. And V2 by V1, I1 by I2, it can be considered as external ratio when the transformer is connected to supply. Here we are considering K underneath bar. That means here we are taking secondary voltage on the top and the primary voltage at the bottom. Here K is greater than 1 means the transformer is step up transformer. K is lesser than 1 means the transformer is step down transformer. K remains always constant. The voltage per turn ratio, it is same for primary and secondary. Transformer core is mainly made up of iron, RGO, heat steel laminations. These laminations are approximately 0.6 mm. All these laminations are stacked together along with insulation in between them. This insulation can be paper, varnish, mica, any other insulating material. These laminations are provided in order to minimize eddy current losses. So the transformer core is completely laminated along with insulation and it is stacked together. Windings are placed on both the limbs. HV winding on limb 1, LV winding on limb 2 can be placed, or else 50% of LV winding and 50% of HV winding. These windings can also be placed on each limb. Here we are representing windings are placed on both the limbs, N1 and N2. N1 is we are considering as primary winding, number of turns N1, secondary winding, number of turns N2. Primary winding is connected to supply voltage V1 and it draws current I1. E is the back EMF. I1 is the leakage flux with reference to primary winding. I is the total flux in the transformer core. E is the back EMF on the secondary side. I2 is the load current. Z is considered as load. V2 is the secondary terminal voltage. Primary and secondary, these two windings are magnetically coupled, electrically isolated. So the electrical resistance between primary circuit and secondary circuit are infinite, R equals to infinite. The magnetic coupling, when the LV winding and HV winding are primary winding or secondary winding, when these two windings are placed very close together along with insulation, then the coefficient of coupling can be nearly 1. If the windings are placed far away, then the coefficient of coupling is 0. This depends upon distance between the windings. Coming to flux in the transformer core. Here we are considering that load is connected on the secondary side of the transformer and supply voltage V1 is connected on the primary side of the transformer. E1 and E2 are respective back EMFs, N1 and N2 are respective number of turns. When the transformer is no loaded, that means there is no load connected on the secondary of the transformer, then the transformer draws only no load current I0. When the load is connected to the transformer, then I2 is consumed by the load. Corresponding current on the primary side is I0 plus I2 dash. As the load increases, loads are connected in parallel. As the load increases, it draws more current, I2 dash. Correspondingly, it draws even more current from primary side, that is I2 star dash. This is I2 dash. This is corresponding to first set of load. I2 star dash is current corresponding to second set of loads. Coming to fluxes in the transformer. When there is no load on the transformer, then the primary current is only no load current I0. This no load current will cause flux in the core, that is flux phi. As the load is connected on the secondary side of the transformer, this load current I2 will cause a flux phi 2 in the transformer core. And that corresponding primary side current I2 star, which causes flux phi 2 dash. This flux phi 2 and this flux phi 2 dash, these two fluxes are equal and in opposite directions. So these two fluxes will cancel each other. Similarly, for the second set of loads, the secondary current is I2 star. This will cause flux phi 2 star. And the corresponding primary side current is I2 star dash. This will cause flux phi 2 star dash. These two fluxes also equal and in opposite directions. So as the load increases, the load current and the corresponding primary current, these two currents will induce fluxes which are equal and in opposite directions. So these two fluxes will get cancel each other. So finally, the net flux in the transformer core will be only phi, which is equal to caused by the no load current I0. So flux in the transformer core remains constant from no load to full load. This is very, very important statement. Flux in the transformer core remains constant from no load to full load. This is the representation here. This is our transformer KVA, and one side we have connected supply voltage, on the other side we have connected load. Thus load is equal to 50% of our transformer rating. Then it is only draws I2 current. And we have increased the load and we have added 20% extra load. That means now the total load on the transformer is 70% of load. This second set of load will draw current I2 star. And we have added the remaining 30% of load. This 30% of load draws I2 double star. So in this way, the additional currents will cause additional fluxes and the corresponding primary currents will cause opposite fluxes. All these fluxes will get cancel each other and the final flux remains in the transformer core is always constant, that is the flux caused by the no load current I0. The flux in the transformer core is not affected by voltage regulation, efficiency and power factor. The flux in the transformer is always independent of all these factors: voltage regulations, efficiency, and power factor. EMF equation. The flux in the transformer core is alternating flux phi. Phi of t equals to phi maximum into sin omega t, sinusoidal waveform. As the frequency is 50 Hz frequency, so the time period is 20 millisecond. For half cycle, the time is 10 millisecond. The maximum values are phi max in positive half wave and phi max in negative half wave. And the time period is 0 to pi first half cycle, pi to 2 pi second half cycle. This is total 1 cycle. This is the flux in the transformer core. EMF will be generated only when there is either relative space variation or relative time variation. The relative space variation is in case of rotating machines. These are the important formulas with reference to EMF equation. E average per ton 4 pi f, E RMS per ton, form factor into E average 4.44 into phi f. So the voltage we are calculating is RMS voltage. E1 equals to 4.44 pi f n. This is corresponding to primary. Similar equations can be derived for secondary side of voltage. This formula can be modified as, from the equation it is clear that the induced voltages are directly proportional to frequency. If we multiply with current on both sides, kVA is directly proportional to frequency. kVA rating is directly proportional to maximum flux density, net cross-sectional area of the core, and the frequency of the flux. B flux density, that equals to flux per unit area. AN is a net cross-sectional area. That means excluding insulation. So these are the important formulas with reference to EMF equation. You have to remember these two important points. Wherever current comes, then we have to consider cross-sectional area of the conductor. Wherever voltage comes, we have to consider insulation. Transformer and DC supply. This is DC supply that is given to transformer. DC supply means flux is 0, so current is constant and flux is also constant. That means rate of change of flux or rate of change of current is 0. So the back EMF induced in the coil or windings is 0. So the windings are having very low resistance. This is the voltage equation for the primary side. V1 equals to E1 plus I1 R1, where back EMF E1 is almost equal to 0. So the current will increase. As the voltage becomes 0, current will increase. The primary will draw high currents from the source. So these high currents either may damage the winding insulation and windings also. So as the transformer windings are having low resistance and high inductance, it draws very high currents from the sources. So in order to avoid such cases, that special designs shall be provided to operate the transformers and DC supply also. The special case means the winding resistance has to be high and the inductance has to be low. By providing this kind of special windings, the transformers can also be operated on DC supply.